Hello, in this video we will talk about molar enthalpy of formation. So the background here is this enthalpy change for a reaction is a really useful number because it tells you how much heat is going to get released or absorbed by the reaction when you're at constant pressure, and we're usually at constant pressure. So delta H is really useful. It'd be nice to be able to calculate that for any reaction without having to run the reaction and measure it, which can take some time. Well, if we knew what the actual enthalpy was, just H and not delta H, then we could take the two actual enthalpy values and just subtract them, right? Final minus initial, and we could figure out what delta H was. But the true value of enthalpy is intractable to measure. It doesn't really conceptually make sense for us to measure it. However, we could find relative values. The actual enthalpy for this compound is some number relative to a standard state. The enthalpy for some other compound is a different amount away from this standard state. And then we can use those relative values to compute enthalpy changes of a reaction directly. So that's what we do. So we set a reference where the enthalpy of formation is 0 for an element in its most stable form. And this is our reference point. So what does this mean? So the degree symbol, like before, it means standard state. We're at 1 bar for solids, liquids, and gases, and 1 molar for solution concentration. And then this F means formation. Formation of 1 mole of compound from its elements. So this is how we reference everything. Elements are 0, and then any compound that you make from those elements, there's some enthalpy change in order to form it. And then once you know those values, you can compare changes between the enthalpy required to make one compound versus another compound, and you can find relative changes to go between these two compounds. A little hard to say in words, but we'll have some examples that'll hopefully make more sense. So do keep in mind that down on the bottom of the slide, for example, that different forms of an element may have different enthalpy of formation values. So in some cases, you've got to be told which state is the standard state. Usually you can just assume if it's the element just by itself, it's going to be 0, but that's not always the case, and graphite and diamond are a notable example of this. Okay, so what do these enthalpy of formation values look like? So if you have a reaction that makes carbon dioxide from graphite and oxygen, these are both the elements in their most stable state. So you're forming the carbon dioxide from this reaction. The enthalpy change of this reaction that we just wrote is the enthalpy of formation, because it's a specific reaction that we defined that the enthalpy change is the enthalpy of formation. So enthalpy of formation of carbon dioxide is the enthalpy change of this reaction that we just wrote on the left. The same is true for water. You make water out of hydrogen and oxygen. Your enthalpy of this reaction is equal to your enthalpy change of formation for water, and it has this value here. So here's a hopefully helpful graphic. So on our y-axis we have enthalpy of formation, and then this 0 line here is representative of elements in their most stable states. Now from that, if you make CO2 out of carbon and oxygen, well, that's an exothermic reaction, and so the enthalpy of formation for CO2 is negative. Whereas if you make acetylene out of carbon and hydrogen, that's an endothermic reaction. So the enthalpy of formation for acetylene is a positive number. Now the true power of doing all this work comes when you want to know the enthalpy change of burning acetylene and forming water and carbon dioxide. You can use these enthalpy of formation values to give you the enthalpy change of this overall reaction without having to do any measurements. That's useful. Now, a note about the standard state here is our choice of defining enthalpy of formation equals 0 for elements in their normal physical states is an arbitrary choice. It's a rather convenient arbitrary choice, but it's still just arbitrary. The same thing is true when you're defining elevation. If you look at Mount Everest, the height of Mount Everest, above sea level, Well, that's kind of our standard metric for elevation. So you'll list the height of Mount Everest relative to the level of the oceans. Well, say instead we chose the lowest point on Earth, the surface of the Dead Sea, as our standard. Well, now the distance to Mount Everest is now 420 meters taller because we set our reference to be 420 meters lower than the previous reference. So then all the elevations on Earth would change by this amount, depending on what we set our reference to. Okay, so enthalpy of formation values are things that you can look up. When you do the homework or work on the test, you'll be given enthalpy of formation values. In the real world, you can look them up in reference manuals or various books. Your textbook has a shorter table in the chapter and then a much longer table in an appendix. So these are numbers you look up. Now, a couple examples here, and both of which arise from Hess's law, which was in the previous video. So Hess's law makes this all possible because Hess's law says that you can take enthalpy change for some process and divide it up into multiple steps. And so our multiple steps are going from our reactants or products in our reaction to this standard state and then back out of the standard state again. So how do we populate the entries on the table in the last slide? So some compounds you can just measure it directly, and that's pretty straightforward. Others can't be measured directly when you make a compound from its elements, but you can figure out what that would be by using Hess's law. So an example, acetylene. You can't measure the formation of acetylene directly, but you can measure the combustion products of acetylene and the combustion reaction itself. So let's just show this. So you can burn acetylene, and here's the equation for what it looks like when you burn acetylene in oxygen. You make carbon dioxide and water, and this has a well-measured enthalpy change for this reaction. It's very exothermic. Acetylene is used for welding. It produces a lot of heat when you burn it. And then we also know the enthalpy of formation values for the carbon dioxide and for water. And we can say if we know the enthalpy of formation, it means we know the enthalpy change for the reaction that goes from the pure elemental states to the carbon dioxide. And here's the enthalpy change for that. Okay, so now we have these three equations. Can we rearrange them to form our overall equation up here? Because that's what we're trying to do. So now this becomes a pretty classic Hess's law problem. And I'll let you pause the video and ponder how to solve the problem. I'll just give you the outcome here. So ultimately, if you double the first reaction and then reverse the third reaction, you will get these reactions to sum up to the overall reaction on the top. And then that means that the overall enthalpy change for reaction 4, which really this is reaction 4 up here, is equal to reaction 1 that's doubled, reaction 2, and then the opposite of reaction 3 because you reversed it. And so you can prosecute that math, and you get this value for the enthalpy change for reaction 4. Now, reaction 4 is the specific formation reaction for acetylene. So the enthalpy change for reaction 4 is the enthalpy of formation for acetylene. So that's something you should know. You should know what it means to have a reaction that represents the formation of the compound from its elements, and that if you find the enthalpy change of that reaction, that's equal to the enthalpy of formation of the compound. Okay, so that's one piece of this. The, if anything, more important piece of this to know is what you do with these values. So you'll get this equation on your info sheet that the enthalpy change of any reaction ever is equal to the enthalpy of formation of its products minus the enthalpy of formation of its reactants. Final minus initial, just like always. Now here, it's written in the equation as just these square brackets around reactants and around products. But what that means is it means that you add all the species together, multiplied by their stoichiometric coefficients. So perhaps an example is best here. So we have our simple example. You're burning methane to produce carbon dioxide and water. And here are the enthalpy of formation values for each of these. Methane, carbon dioxide, and water in the gaseous form. the enthalpy of formation for liquid water is different because there's an energy change when you go from the liquid to the gas, and so you have different enthalpy of formation values. And then not listed here is that the enthalpy of formation for oxygen is 0 because it's a pure element in its lowest energy state. So it's 0. And so that's not usually listed in tables, you just have to know that. Okay, so we take the products over here, and if we look at our products, we have 2 times water, because there's 2 waters in the balanced chemical equation. And then we have carbon dioxide right here. So 2 times the enthalpy of formation for water plus the enthalpy of formation for carbon dioxide. That's the left side. And then on the right side is all the reactants. And so we have the enthalpy of formation of methane here, because it's one of the reactants. And then we have 2 times the enthalpy of formation for oxygen, because there's a 2 right here. Mind you, enthalpy of formation for oxygen is 0, but I'm going to include it here so that hopefully it all makes some more sense. Now, the square brackets are useful because we're subtracting this right here. So that means we need to subtract methane and subtract oxygen. So it's easiest to wrap this in square brackets and make sure you get the sign dealt with correctly. Now we can plug numbers in for this that are given right above. Remember, oxygen is 0. And then we get our answer. So the delta H of this reaction is negative 802.5 kilojoules per mole. And that's the great power of the enthalpy of formations, is that you can use them to figure out the enthalpy change of any reaction, assuming you know the enthalpy of formation values for all the components of the reaction. Okay, so a final example. Benzene burns in air to produce carbon dioxide and water, and this problem is specifying liquid water. Okay, and then let's calculate the enthalpy change or reaction for this. So you're given the standard enthalpy of formations for your various products and reactants. And now in the problem, they're nice enough to give you this fact that the enthalpy of formation of oxygen is 0. But don't always count on being given that. Sometimes, to make the problem a little harder, to test your knowledge of the material better, you're not given that value, and you're left to ponder what the heck it is. So you need to know that it's 0. Okay, and here's the overall balanced equation here. And you can even phrase this as a multiple choice question, because aside from some algebra and a little bit of concept here, the ultimate execution of this is fairly straightforward. So let's try it. So here's the equation. Your enthalpy change of your reaction is the products minus the reactants, final minus initial, and you'll be given this equation, but you need to know how to use it. It's not very self-explanatory. What you have to do is you have to take the products multiplied by their stoichiometric coefficients. So here's the CO2, here's the water, and then you subtract from that the reactants. So here's the benzene, and there's 2 benzenes in this balanced equation, and then here's the water. 15 times 0. So I just wrote it as 0 here to save a little bit of space. Okay, now that you know this, you can plug the numbers in from the problem. And each one of these is kilojoules per mole. And it's probably a good idea to put the units in when you do this math. I omitted it so that it would be less cluttered on the slide here. All right, and you solve this out, and you get negative 6,535 kilojoules per mole for the reaction listed in the problem, the combustion of benzene. So once you know how to use this formula, the outcome of this is pretty straightforward. Just plug the numbers in and get an answer. And that's awesome. That's the power of using these enthalpy of formation values. Okay, and that's all we have for this video. Thanks for watching.